Hi again everyone. In this video we're going to have an introduction to double integrals and we're going to discover how to integrate over rectangular regions. Now double integrals are just a generalization of the basic single integral that you would have seen at high school. Now here's an example of a double integral. You can see there are two integral signs, two differentials, and the integrand, or the function we're integrating, is a function of two variables, x and y. Now, double integrals enable us and empower us to work with more complicated problems, more sophisticated functions, and we're working in higher dimensions here. In particular, double integrals find many interesting and important engineering applications. For example, if we're studying the properties of thin metal plates, then we can use double integrals to calculate the centre of mass and the moments of inertia from a known density function. But this video is just a very simple illustration of how to calculate the double integral, and we'll talk a little bit about notation and the geometry of the region of integration. So let's consider the following example. Now, as a general rule, this kind of repeated or iterated integral can be thought of as one integral inside another integral. Okay, now just like the single integral case, we have limits of integration. However, the region of integration for double integrals is more complicated than the region of integration you would have seen at high school. Now at high school you would have integrated a function, say from x equals 1 to x equals 4 or something like this. It's important to understand that the region of integration for single integrals is just an interval. However, with double integrals, the region of integration, as illustrated by these upper and lower limits, is a two-dimensional set. In this case, it's a rectangle because we have constants in both the upper and lower limits of integration in both integral signs. So the first thing I'm going to do is sketch the region of integration, and in general it's important to sketch the region. This is a very simple example, so it's actually not necessary here, but for very complicated integrations it's important to sketch the region because the region of integration has a much more significant role in the computation actually setting up the integral in the first place than the single integral case. So let's realize that our region of integration is a rectangle, and you can see from the way, like you can think of this as an outside differential and an outside integral sign, an inside differential and an inside integral sign. Now it's important that you team those up because they give you the bounds on the region of integration. So x, it would be between 1 and 3, and y would be between 2 and 3. So if I just draw in my region, my little rectangle in the xy plane, what I'm going to do is draw in the line x equals 1, x equals 3, and the line y equals 2, y equals 3. And you can see those four lines bound or enclose, in this case, a rectangular region. So this shaded area is our rectangular region that we're integrating this function over. So how do we actually perform the double integral? Well, a good general rule is to try to consider the inside integral first and just integrate with respect to y, holding x fixed. And then after you've done that, move to the outside integral and integrate everything with respect to x. So let's write down a note about the method. Okay, evaluate the inside integral first, and then move to the outside integral and evaluate that. So let's see how that works in practice. So I'm just going to write out the integral again, just so all the calculations are on one page here. Okay, so if I put in my brackets and just consider the inside integral, what I do is, because we have a dy here, I hold x fixed and integrate each term with respect to y. Okay, so x squared will become y x squared, minus 2xy will become minus x y squared, and 2y cubed will become y to the fourth on 2. And because it's a definite integral, we have to remember to make the appropriate substitutions for the limits of integration. So now we sub in for y equals y equals 3 and y equals 2. So I'll get 3x squared minus 9x plus 81 on 2 minus, substitute y equals 2, 2y squared minus 2x squared minus 4x plus 8. So now I've reduced the calculations to a single integral, and all I need to do is clean up this integrand. So let's do that. So now it's just a single integral that we recognise. So let's integrate this and then we'll be finished. So now it's just substituting in these values and a little bit of arithmetic. So I'm not going to bore you with all the calculations here. And just cleaning up here, you'll get 53 and 2/3. So we have solved our problem. But let's have a look at the bigger picture. So the first general point is about method. When you're evaluating a given double integral, perform the inside integral first and then move to evaluate the outside integral. Now something on notation. The general way of writing a double integral over, for example, a rectangular region is this notation here. Now the dA is called the area element, and you can think of dA as being dx dy or dy dx. The order is not necessarily fixed. Now, in this second point, Fubini's theorem says if we have a continuous function on a rectangle and we're integrating the function over that rectangle, then you can switch the integral signs and switch the differentials and produce the same answer. So let me put that in a bit of context. if we switch these integral signs, switch these differentials, and then evaluated the integral in the normal way, we would still get the same answer of 53 2/3. Now, although this example was very simple, it is generally a good idea to sketch the region of integration so as to better understand the geometry of the problem. I'm going to leave you with the following question. Can you give a physical interpretation of the double integral related to, for example, volume of a specific solid or shape? I've also left you with two examples. These are very similar to the example that I've solved, so have a go at those and learn by doing.